Now we will take a look at a few examples. The first example, a force acting on a particle moving in the xy plane is given by 2y I hat plus x square j hat, where F is in newtons and x and y are in meters. The particle moves from the origin to a final position having coordinates x equals 5 meters and y equals 5 meters as shown in figure. So we go from origin to this point C, which is at 5, 5. Calculate the work done by F on the particle as it moves along the purple path, that would be this purple path, OAC, the red path, OBC, and the blue path, OC. Is F conservative or non-conservative? Explain your reasoning. Okay, so let's start with part A. We're moving along the purple path, OAC. So work done by this force F from point O to point A plus the work done from point A to point C along this purple path is basically the total work done going from point O to point A to point C. So we can start with work done going from point O, origin, to point A along the purple path. So this is the integral. We're going from x equals 0 to x equals 5, 0 to 5. The force 2y I hat plus x square j hat, dot product with our incremental displacement vector. Since we're moving on the x-axis, this would be dx I hat. So this integral will become from 0 to 5. Because j hat dot I hat is 0, we will have 2y dx, and this will give us 2y times x evaluated between points 0 and 5. So this is basically 10y. But along this path going from point O to point A, y is equal to 0. So I find that the work done from point O in going from point O to point A is 0 joules. Okay. Now we're going to go from point A to point C. So we will be moving along this path where x is fixed at 5 and y is changing from 0 to 5. Work done going from point A to point C. This will be the integral. Y is changing from 0 to 5. X is a constant. So we have 2y I hat plus x square j hat dot product with our dr vector, which is dyj hat, because we're moving on the y-axis. So this is going to give us integral 0 to 5. Because I hat dot j hat is 0, only the j hat dot j hat will give us an answer, x square dy. So this is an integral over y, so this will give us x square y evaluated between y is equal to 0 and y is equal to 5, which is 5x square. So this is y equals 0 to 5. Now, along this path, x is equal to 5 on the path from A to C. So we find that the work done in going from point A to point C along the purple path is basically 5x squared, 5 times 5 squared, which is 125 joules. Then we can add these two contributions. Work done along the purple path going from the origin to point A to point C is 0 plus 125, that is 125 joules. Okay, now we're ready to calculate the work done on a different path. So in part B, we want to calculate the work done along the red path, going from O to B to C. So O to B to C. First, we're going to have x equals 0. Y will be changing from 0 to 5. Then we will have y equals 5. X will be changing from 0 to 5. Okay, so let's start with going from the origin to point B. And then we will go from point B to point C. This will give us the total work done in going from point O to point B to point C along the red path. Okay, so let's start with point O to point B. Once again, we have integral f dot dr. Now, along this path, we have y changing from 0 to 5. The force was 2y I hat plus x squared j hat, dot product with our dr vector, which is dy j hat on this path. And j hat dot j hat is 1, I hat dot j hat is 0. So this will be an integral from 0 to 5 x squared dy. So this will become x squared y, changing from 0 to 5. So that's again 5x squared. But we still have x equals to 0 on this path from point O to point B. So we find that there is no contribution from the motion from point O to point B. It's 0 joules. Now we can calculate the contribution from point B to point C. Now we have x is changing from 0 to 5, 2y I hat plus x squared j hat, dot product with dr. Once again, so we're moving on the x-axis. So x is changing from 0 to 5. We have dx I hat as our incremental change in position vector. So this will be integral from 0 to 5. Only contribution comes from I hat dot I hat, so this becomes 2y dx, and that is 2xy. X is changing from 0 to 5, that is 10y. And on this path, y is equal to 5. Going from B to point C, therefore we find that the work done in going from point B to point C on the red path is 10y, which is 10 times 5, 50 joules. So we find that the total work done going from point O to point B to point C on the red path is 0 plus 50, which is 50 joules. Now let's do the blue path. The blue path, we're going directly from point O to point C. So now I have to find out what is the incremental displacement vector here, dr, which is in general given as dx I hat plus dy j hat. Along this path, I want to know the relationship between x and y. I go from 0, 0 to 5, 5 on a linear path. Therefore, this is y is equal to x line. So I find that dx should be equal to dy. So x equals y implies dx equals dy. So I find that my dr vector is dx I hat plus dx j hat. So that's one way to write it. Okay, now we can calculate the work done from point O to point C, integral 0 to 5, x is changing from 0 to 5 and y is also changing from 0 to 5, but so this is 2y I hat plus x squared j hat dot product with the displacement vector dr, which is dx I hat plus dx j hat. So I'm going to find from this dot product I hat dot I hat is 1, so there will be a 2y dx, and j hat dot j hat is 1, so this is going to be 2y plus x squared dx. But then I find y and x are equal along this path, so we're moving on y equals x. So this is x squared plus 2x dx. This integral will give me x cubed divided by 3 plus x squared, which is to be evaluated between x equals 0 and x equals 5. So I find that the work done in going directly from point O to point C is 5 cubed over 3 plus 5 squared, x cubed over 3 plus x squared, where x is 5. So we find this is 125 divided by 3 plus 25, which is 66.7 joules. So let's take a look at part D. So we have found 3 different values: 66.7 joules, 50 joules, and 125 joules. We're achieving the same task, go from point O to point C. And depending on which path we take, we're finding a different value for the work done by this force. So is F conservative or non-conservative? Explain your reasoning. Okay, so I can say that since the work done going from point O to point C directly is not equal to the work done going from point O to point B to point C, is not equal to the work done going from point O to point A to point C, we can conclude the work done by this force F depends on the path taken. So therefore this force F is a non-conservative force. It's non-conservative. Now I want to take a look at the other property of conservative forces. Conservative forces should be derivable from a potential energy function. So let me try to derive this force from a potential energy function. 2y I hat plus x squared j hat, is this equal to minus del u del x I hat minus del u del y j hat? So this equality will give me minus del u del x is equal to 2y, which means, and minus del u del y is equal to x squared. So this is going to tell me the potential energy function should be of the form 2xy plus possibly a constant c. And this tells me the potential energy function should be of the form x squared y plus a constant c. So since I have x squared y not equal to 2xy, u of xy does not exist. Therefore, the force F cannot be derived from a potential energy function u of xy, so it must be non-conservative. So this is an alternative way of seeing if this force is conservative or non-conservative. If I find that the work done depends on the path taken, it must be non-conservative. If I find that it cannot be derived from the potential energy function, that also implies it is a non-conservative force. Okay, so let's summarize what we said here. We are going along 3 paths. The purple path, where x is changing from 0 to 5 first, and then y is changing from 0 to 5 at x equals 5. And then the red path, y is 0, x is 0, y changes from 0 to 5, y is 5, x is changing from 0 to 5. And then we go along y equals x line, going from 0 to 5. So I calculated the work done on these paths by considering the portions of the path separately, and I find that the purple path gives me 125 joules, the red path gives me 50 joules, the blue path gives me 66.7 joules. Since the work done depends on the path taken, it is non-conservative. I also checked if it can be derived from a potential energy function. It's clearly not possible to derive it from a potential energy function u of xy. Therefore, this force is non-conservative. Okay, let's move on to another example. A block with mass m, initially at rest, is pulled to the right along a frictionless horizontal surface by a constant horizontal force of magnitude f. Find the block's speed after it has moved through a horizontal distance delta x. So I'm going to calculate the work done by this force F. It is the integral from 0 to delta x. The force is applied in I hat direction, f I hat dot dx I hat. So I'm assuming that this is my x-axis. And that's basically f times delta x, because f is a constant, it comes out of the integral. Now I find that the net force acting on the x-axis is f, which is equal to mass times acceleration. So I can use work kinetic energy theorem. Work kinetic energy theorem applies, and what does it tell us? The work done by this force F is the change in the kinetic energy of the system. What is the final kinetic energy? 1 over 2 mv final square. What is the initial kinetic energy? Because it was initially at rest, it is 0. So this is going to be equal to f times delta x. Therefore, we find that the final speed of this block should be 2f delta x divided by m square root. Now we make a modification. We have a coefficient of kinetic friction with the horizontal surface mu k. So F is not the only force acting to the right. There is a kinetic friction on the x-axis which is opposing the motion. So this is my y-axis, this is my x-axis. The net force on the y-axis must be equal to 0. As you can see from this diagram, we have the normal force and the weight acting on the y-axis. So normal force N minus mg must be equal to 0 because there is no motion on the y-axis. The normal force must be equal to mg. Then the kinetic friction must be equal to coefficient of kinetic friction times the normal force, which is mu k mg, which is opposing the motion. Okay, so what is the net force acting on the y-axis? F net x component. It is the force F minus the kinetic friction, which is F minus mu k mg. The net work done on the system is the change in the kinetic energy of the system. So I can say that the net force F minus Fk times delta x, the work done by the net force, is 1 over 2 mv final square minus 0. So F minus mu k mg, the net force on the x-axis, times delta x is equal to 1 over 2 mv final square. So the final velocity is modified. It is 2 f minus mu k mg delta x divided by m square root. So in this case, we have a modification on the problem. There is an energy loss. The energy loss is in the amount of kinetic friction times delta x, and this happens because the kinetic friction is a non-conservative force. The mechanical energy, part of the mechanical energy is converted to heat. So it goes to heating the interface. One more modification. Now we're back to zero friction, but the force is applied at an angle theta with respect to the horizontal surface. What would be the answer in this case? Well, the work done by this force is integral 0 to delta x force dot product with displacement dx I hat, which is integral 0 to delta x f cosine theta dx. This is a constant force, so it comes out of the integral with the constant angle. So f cosine theta delta x. The work done by this force, because it's the only force acting on the x-axis, is equal to the change in kinetic energy of the system. F net x component is equal to f cosine theta, which is mass times acceleration. So f cosine theta multiplied by delta x must be equal to the change in kinetic energy 1/2 mv final square minus 0. So I find that the final speed should be 2f cosine theta delta x divided by m square root. Now we have seen three possible scenarios. We have a block that is being pulled to the right with a constant force F. So if this is the only force acting on the x-axis, there's no friction. The work done by this force, F times delta x, is equal to change in kinetic energy of the system. Also, you see that there is no change in the y-axis position. So there is no change in potential energy of the system. So the change in kinetic energy is the work done by F, which gives us the final speed. If we add kinetic friction, this final speed will be reduced because part of the energy will be lost to heat. How can we calculate the final speed in this case? If you write the net force acting on the x-axis, F minus Fk, where the kinetic friction is mu k times the normal force mg, the work done by the net force on the x-axis is the change in kinetic energy of the system in the work kinetic energy theorem. So we can say that the final speed is reduced. Now, why was it reduced? Because this kinetic energy, part of the kinetic energy that was given by F is now converted to heat. It is lost to heat because the kinetic friction is a non-conservative force. If we have no friction but apply F at an angle, then we have to consider the projection of F onto the x-axis, which makes F cosine theta delta x work, but the projection on the y-axis does not do any work. That will just modify the normal force acting on the surface, on this block, and therefore we find that F cosine theta equals ma, and F cosine theta delta x, work done by the x component of the force, is equal to the change in kinetic energy of the block. Okay, now let's move on to the last example for this video. A uniform board of length L. Uniform board of length L is sliding along a smooth, frictionless horizontal plane as shown in the figure. The board then slides across the boundary with a rough horizontal surface. This is where it starts. The coefficient of kinetic friction between the board and the second surface is mu k. Find the acceleration of the board at the moment its front end has traveled a distance x beyond the boundary. The board stops at the moment its back end reaches the boundary, as shown in figure. The final speed is 0. Find the initial speed of the board. Now, so in part A, we see that the board moves a distance x beyond the boundary, and we want to know the acceleration at that point. So this is our scenario. This is our rough surface. We have kinetic friction coefficient mu k here for this rough surface. And we have a uniform board. So what is the meaning of having a uniform board? That means the mass is distributed uniformly across this board. So if we calculate the mass per unit length, mu, mass per length, it is the total mass of the board divided by the total length of the board. So as for the portion that has crossed the boundary, the portion across the boundary will have a mass, let's call it m prime, which is mass per unit length times the distance we have traveled x. So it is m over L times x. So that is the mass of this portion. This has mass m prime. Okay, now I want to draw the free body diagram for the portion across the boundary. Or the portion that has crossed the boundary. So this is modeled as a particle with mass m prime. I have a normal force acting on it. I have the weight acting on it. Normal force, the weight m prime g, and the kinetic friction, which is opposing the motion. Since the motion is to the right, the kinetic friction force is to the left. And let's call this y-axis, this x-axis. The net force on the y-axis must be equal to 0 because the normal force must be balancing the weight. There is no motion on the y-axis. So I find that the normal force is changing as a function of s as m prime g, because m prime is a function of x. It is m over l x g. The kinetic friction force is the coefficient of kinetic friction times the normal force n, which is mu k times m prime g, which is mu k times m gx divided by L. And it's pointing in minus I hat direction. So what is the net force acting on the x-axis? It is minus Fk, which is equal to mass times acceleration. So I find that the acceleration is minus Fk magnitude divided by m, which is minus mu k mgx divided by ml. M's will cancel, so I see that this board will be decelerating. The acceleration is negative, minus mu k gx divided by L. So at the moment its front end has traveled a distance x across the boundary. The acceleration is minus mu k gx over L, and it is basically decelerating. It has an initial speed v, as you can see here, and final speed 0, therefore it must be decelerating as it moves across the boundary, and this is what I find. There is a deceleration. Acceleration is minus mu k gx over L. Part B, the board stops at the moment its back end reaches the boundary. Find the initial speed of the board. So this is the final situation, this is the initial situation. So I want to know the work done by the net force acting on the system must be equal to change in kinetic energy of the system. The net force acting on the system is minus Fk, so it's the integral. X goes from 0 to L, minus Fk I hat dot dx I hat, which is integral from 0 to L minus mu k mgx over L dx, which is minus mu k mg divided by L. The integral of x dx is x squared over 2. Evaluated between 0 and L, this becomes minus mu k mg L divided by 2, because one of the L's will disappear, and that must be equal to change in kinetic energy of the system. So final kinetic energy minus initial kinetic energy, 0 minus 1 over 2 mv squared, must be equal to minus 1 over 2 mu k m gl. So 1 over 2's will cancel, m's will cancel, and I will find that the initial speed was square root mu k gl. Now what has happened here is, because the kinetic friction is non-conservative force, there's a change in the mechanical energy of the system by an amount delta K, which is transferred to heat. So it acts to heat the system. as we lose the kinetic energy to friction. Okay, so to summarize, in this example, we have a uniform board. Mass is distributed uniformly on this board. Mass per unit length is total mass divided by L for any portion of the board that has a length x. The mass is m over L, mass density times x. So that's what it means. And for the portion of the board that has traveled a distance x across the boundary, we have looked at the free body diagram. We see the normal force from the horizontal surface, the weight of that portion, and kinetic friction acting on it. The normal force is a function of x m prime g, which is m over L x g. The kinetic friction is opposing the motion in negative direction. It is mu k m g x over L. And the net force on the x-axis is this kinetic friction minus Fk, which is mass times acceleration. So we find the acceleration is negative, minus mu k gx over L. It's decelerating. The work done by the net force is equal to delta k. So even though I write it this way, it doesn't imply that the kinetic friction is doing work. In fact, we find that it is causing an energy loss. So there is no work done on the system. The work done by the net force turns out to be minus mu k mgl over 2, which is equal to change in kinetic energy of the system. So we find that this kinetic friction is causing a decrease in the kinetic energy. There's no change in potential energy because y is a constant along this path. And the mechanical energy is converted to heat. And in this process, the change in kinetic energy is equal to minus 1/2 mu k mgl. So we find that the initial speed should be square root mu k gl for this to be possible.